Hey guys, it's Jessie. I wanted to post a quick video to help you with Lab 6. I'm going to dive into Activity 3 because I'm assuming that Activity 2 with the balloons wasn't too bad. I hope that's the case. Okay, so Activity 3 is very similar to the balloons, except that we're going to use these model pieces to represent really the same thing. The balloons were representing the electron valences, where really what we have here are the atoms themselves. Each prong would be a bond, and these are your lone electron pairs if you have those. So the key here is to find a central atom that has the same number of prongs as bonds or valence electrons, that you're trying to represent here. So this one has 5. You see there's one on the top, one on the bottom, and then 3 around the side. This one has 6 on the top and the bottom, and then 4 around the sides. And then this is like the tetrahedral geometry. There's 4 prongs. And the idea is then you just add your bonds and your other atoms, and you get a really good spatial representation of what that looks like. So then it does also ask you to sketch this. Your book gives some good examples of how to do that, as does your lab manual, but let's just go ahead and sketch an octahedron. Sulfur hexafluoride, I guess, is an example. So sulfur is our core, and I'm going to have 6 bonds coming off of that. So the dashed lines indicate that they're moving towards the back or into the page, and then the little wedges indicate they're coming out of the page at you. So and there's all my fluorines. Here's how I draw it on the page. Here's what it looks like. Oh, except this would also have to be turquoise because they're all the same, but you get the idea. Okay. Activity 4 is simply asking you to complete this data table. Let me scroll down of electronegativities. It gives you a bunch of different molecules. Yeah, and you just need to find the different electronegativities of each atom, and that will tell you what kind of bond it is, because you look at the 2 electronegativities, subtract them, and use your sliding scale here, whether it's nonpolar, covalent, polar covalent, or ionic, based on the difference in electronegativities. And those are all provided in the book for you on figure 6.6, if that helps. Okay, that's activity 4. Activity 5 is very similar to activity 3 at the modeling, except we're specifically looking at carbon. So carbon's going to be one of these tetrahedrons, and in its most simple form, it's bonded to 4 hydrogens, so that's called methane, and that would look like this. And then if you're going to bond it to another carbon, it would also have 4 hydrogens, but it would drop one of those and come over and bond to your carbon. So that would look like this. Or maybe get a double bond, and that would look, you can represent that as well. And you can continue to make long chains, which is what activity 5 is asking. Okay, and then the last, well, it's activity 2, I guess, but it's this data table, this one. So let's go ahead and complete methane, I guess, as an example. You need to do this for 9 different ones, 3 from each group, but we'll do methane quickly so you guys can see. So methane is, again, carbon, which has 4 electrons in its valence shell, and 4 hydrogens, which has 1. Okay, if we put them together, it's gonna look like this. Or that 3D structure would look like this. And then I just need to look up the electronegativities. Carbon is 2.5, hydrogen is 2.1, for a difference of 0.4, which on our scale is a non-polar covalent bond. And since it's non-polar, there's no dipole moment. There is some bond polarity actually towards the carbons because you know, there's more protons, so it's pulling them a little closer. You can do that on each of those. That should help you with your lab. You guys have my phone number. Please feel free to call me or text me, and you're always welcome to email. Thanks.